what, million, 10 million, 100 million, depends on how big computers and data sets you got. So n can be huge. D, the dimensionality, the vectors that we are working with, the raw vectors, that can also be pretty large. Think if X is an image, if it's a megapixel image, wow, D is like a million already. If you're somebody like Criteo or Facebook or Google and you're serving web advertisements, D, these are the features, could be like in several hundred million, even a billion, where they encode all sorts of nasty stuff and information they collect about you as users. So many nasty things they can collect, right? So D and N are huge. And it's because both D and N are huge, we are interested in thinking of optimization methods for large-scale machine learning that can handle such big D and N. And this is driving a lot of research also in theoretical computer science, including the search for sublinear time algorithms and all sorts of data structures and hashing tricks just to deal with these two quantities. So here is an example, super toy example. And I hope really, by that I can squeeze in a little bit of a proof later on towards the end. I'll take a vote here in class to see if you are interested. Let's look at the most classic question, least squares regression. A is a matrix of observations, or sorry, measurements. B are the observations. You're trying to solve ax minus b whole square. Of course, a linear system of equations, the most classical problem in linear algebra, can also be written like that, let's say. This can be expanded. Hopefully, you are comfortable with this norm, right? So x2 square, this is just defined as